Hi class, in today's video we're going to be talking about section 1.6, inequalities. And so what is an inequality? Well, whenever we replace the equal sign in any equation, so when we replace the equals sign in any equation with one of the four inequality signs, one of the four inequality signs, and I'll talk about them in just a second. The resulting expression is an inequality. So remember, an expression is just some combination of terms, whether they're constants, variables, or something like those. And then to make that an equality or an equation, we introduce the equal sign, right? And so that's where instead of just negative 2x, we had negative 2x equals something. Well, if instead now we start with one of those equations, so there's an equal sign, and we replace that with one of these four. We have this one, this one, this one, or this one. And so we call this the less than, this one the greater than. The third is the less than because it has the same arrow, but now that there's a line under it, that's our less than or equal to. And then our last one is greater than or equal to. Again, because we have our equal sign, right? And so you can think of, we have an equal sign, and then what's happening is we either switch that top one to one of these, or we switch that top one to one of these. Those are my less than or greater than or equal to's. So, but some of the things that we talk about with an equation are still the same. So domain, that's still the numbers for which both sides are defined. Right, so we had, it wasn't necessarily that they were true. Like if you had x equals 4 and you were like, well, let x equal 7. 7 doesn't equal 4, but x is still defined when it was 4. So the domain is still the numbers for which it's defined. The solutions are still the numbers for which it is true. And of course, we'll work through a number of examples shortly. And we will still classify them as one of three things: conditionally true, inconsistent, and remember that's when they're never true, and identity, which was when it was always true. And so let's look at an example. For example, suppose we have 2x plus 2 equals 7. Well, that's an equation because it has an equal sign. And so we can convert that into equality by saying 3x or something, or wait, no, if I could write the same thing. 2x plus 2 is less than or equal to 7. And so now we care about whether or not it's sometimes true, always true, or never true. So first we'll think about domain. Is there any value that you can't substitute in for x? No, the domain is all reals. which looks like negative infinity to infinity with our parentheses. Remember, domain often became something other than all reals when we had a rational equation, so we had something in the denominator, or when we had a radical equation, so that's where we had like a square root or a cube root. And so the domain is all reals. Solutions. So which values of x make this a true equation? Oh, there's my cat's paw. So what values of x make it so that 2 times that value plus 2 is less than 7? Well, before we can solve this, what we'll need to look at are our equivalent operations. So what things can we do to an inequality that preserve the solution set, that preserve the set of values for which it is true? And so let me go to a new piece of paper. I'll give you those 3 equivalence preserving operations. So we have equivalence preserving operations. And once we have those, we're going to go back to our example and find a solution set. And so these will look similar to our equivalence preserving operations we had for equations. We can simplify both sides. We can add or subtract the same expression from both sides. Or we can multiply or divide both sides by a positive number. And I'm going to emphasize that it has to be a positive number. And I will explain why in a little bit, but if it's a negative number, we have to, quote, flip the inequality. So in other words, less than becomes greater than, and vice versa. Less than or equal to becomes greater than or equal to, or vice versa. And so now that we have our equivalence preserving operations, we'll go back to our 2x plus 2 is less than or equal to 7 example. And so we can simplify. Well, 2x plus 2 doesn't simplify, and 7 is just 7. We can add or subtract the same expression from both sides. Well, we can subtract a 2 from both sides, because a constant is an expression. And then we have 2x is less than or equal to 5. And then we can multiply or divide both sides by a positive number. Well, that means we can divide both sides by 2. Nothing changes. We have x is less than or equal to 5 halves. And so that means, let's look at a number line. And I always put 0 in the middle just so we know where we're thinking about our positive integers or numbers and our negative numbers. And so 5 halves is 2 and a half. So 1, 2, 3, so that's 2 and a half, 5 halves. And this says that our solution, x, has to be less than or equal to 5 halves. Well, that means if we mark 5 halves with a solid dot, so that solid dot, if, can be equal. So you will see an example of what that means if that's not the case. And then if that number has to be, x has to be less than or equal to 5 halves. Well, if I were at, say, 3, I would be greater than. But if I were at 2, I would be less than. And so what I will do is I will shade in this side of the number line. And so this side shaded in, and it goes up and stops at 5/2. And then in interval notation, that looks like any number up to and including 5/2 and everything smaller. So set notation. Nope, not set. Interval. Interval notation, or we have our number line. And so what you'll find is as we work through examples, we tend to use our number line to get to an answer, and then we give our final answer in interval notation. So suppose we have this another example. But I want to point something out. We were able to come to a solution here. And remember on my previous page I said we can still classify them as conditionally true, inconsistent, or identity. Well, as long as x is in this interval, it's true. So this one is conditionally true. That means, and I'm going to put this in words, as long as x is less than or equal to 5/2, 2x plus 2 is less than or equal to 7. And if we want to check that, so let x equal 1, 2 times 1 plus 2 equals 5, and 5 is less than or equal to 7. But if we say let x equal 3, we get 2 times 3 plus 2, which is 8, and x and 8, is not, and so we can put a line through that, is not less than or equal to 7. And so that also satisfies this being true. So that's a conditionally true. We'll look at two more, and you might be able to guess what those ones will end up being classified as. But example, if we have 2 times x plus 2 is greater than or equal to 2x plus 4. Remember, we can simplify, so go ahead and distribute that 2. 2x plus 4 is greater than or equal to 2x plus 4. We can add or subtract the same things from both sides. So go ahead and subtract 2x from both sides. 4 greater than or equal to 4. Well, 4 greater than or equal to 4 is always true because 4 is always equal to itself. So this is always true. Therefore, this inequality is an identity. So because always true, we have identity. And then one more example, and these are actually among the least interesting examples we'll do today. If we have x is greater than x plus 4, we'll do the same thing, subtract x from both sides. We get x minus x, which leaves us with 0, 0 greater than 4. Well, is 0 greater than 4? Well, that's never true. Therefore, this inequality is inconsistent. So never true means inconsistent. And so whenever you're given any sort of inequality, what we're likely going to want to do is work down to some statement that either has x greater than, less than, or equal to some number. Or in some cases you'll get a number, let's say greater than, less than, or greater than or equal to, less than or equal to some other number. And what we'll do with that is then we can either decide if it's conditional, or if it's identity, or inconsistent. So we'll look at a couple more examples. Example. Suppose -5 is less than or equal to x is less than or equal to 0. Notice we have two inequalities here. Well, here we have -5 is less than or equal to x, and we have 0 is less than or equal, or x is less than or equal to 0. And so go ahead and graph each of these separately. We have x being bigger than -5. Put a 0, -5. And if we look at just this one, -5 is less than x or equal to, so start here, and it can be anything to the right. Because if we put, say, 0, 0 is bigger than or equal to -5. And if we look at this other one, put our number line, 0, we have x is less than or equal to 0. So, or equal to means we have a solid dot, and x is less than or equal to that, and so we shade everything to the left. And then what we need to do is we need to put them together. So we need everything right of -5 or equal to. And here we need everything left of 0 or equal to. And so if I bring those back together, draw my number line, put our -5 and our 0. It can be right of -5, so this away, and left of 0, this away. And so what we have is that space between. And then equivalently, it can be as small as -5 or as large as 0. Square brackets. Because equal to. I mean, and if we look at this and think about translating this into English, we have x is between -5 and 0. So it's the space between -5 and 0. And another way you might see this represented is instead of doing solid dots and or an open dot, which we'll see in a little bit, some people will do it this way. So we have -5, 0, and they'll put a square bracket and a square bracket, and they'll shade it that way. Because then that reminds us that that square bracket corresponds to that. So I might do it interchangeably just so that you're familiar with both, but I don't have a strong preference one way or another. So another example, suppose we have x greater than 2. We always draw our number line. I always put 0 in just so I know where I'm at. And then I have 2. So x bigger than 2. So like that would be 3 or 4 or 2.5. But notice it's not equal to. So it can't be equal to 2, but it can be bigger than 2. And then our set notation for that is 2 to positive infinity. Well, we can never reach positive infinity, so we always put a parenthesis. But it can't equal to 2, so it's an open. So it's parenthesis because not equal to 2. And so the other way you might see this drawn, 0, 2, is with a parenthesis there, and then shaded in. Look at a couple more. -2x is less than 2. And so if you remember I said we can't divide by a negative unless we flip it. So I'm going to use that process of flipping, and then I'll show you why that's the case. So divide by -2 and flip. So if I have -2x is less than 2, divide both sides by -2. -2 divided by -2 is 1, so we just have x. This less than flips and becomes a greater than, and 2 divided by -2 is -1. And the reason for that is, so suppose we're just going to not divide by a negative. I have -2x is less than 2. I'm going to add a 2x to both sides, and I'm going to subtract a 2. So I'm going to do both of those at the same time. Well, -2x plus 2x is 0, so we have -2 is less than, those subtract off, 2x. Remember, we can divide by a positive number without changing this direction. X is greater than -1. And so if I just rewrite that with the x on the left, x is greater than -1. Right, and so those are the same. It says that x has to be bigger but not equal to -1. So we have -1 not equal to but bigger than. Drawing it on a number line, I always draw my 0, -1, parenthesis, and then to the right. And so that tells us that whenever this x right here is bigger than -1, this will be true. Like if I have -4, I'm going to get 8, which isn't less than 2. If I put a -1, I'm going to get 2 less than 2, which isn't true. But if I have a if I have a 0, I get 0 is less than 2, which works. Or 3, -2 times 3 is -6, which is less than 2. And so we'll work through a couple more of these, and then I'll introduce what are called compound inequalities and conditional inequalities before we work with a little bit more complicated ones. So example, 4 times x minus 1 is greater than or equal to 3x minus 1. So we can simplify first. 4x minus 4 is greater than or equal to 3x minus 1. Go ahead and subtract a 3x from both sides. So we have 4x minus 3x leaves us with 1x minus 4 is greater than or equal to -1. Add a 4 to both sides. X is greater than or equal to 3. Draw our number line, 0, 3. Greater than or equal to means we can fill it in or put a square bracket. Shade everything to the right, which looks like 3 positive infinity. And equivalently, 0, 3, we could fill in the dot and shade it in. So I think we're getting the idea of this one, right? Essentially, we need to think about what these symbols mean in practice and find the values of x for which it is true. Last example of this form, so let's introduce a fraction. 2x minus 3 over 4 is greater than or equal to 3 minus x over 2. So remember, we can multiply or divide both sides by a positive number. So let's multiply both sides by 4. So 2x minus 3 over 4 times 4 greater than or equal to 3 minus x over 2 times 4. Well, if I have 2x minus 3 divided by 4 times 4, those cancel and I'm just left with 2x minus 3, which is greater than or equal to, this one we need to distribute 4 times 3 is 12, minus, if I divide by 2 and then multiply by 4, that's the same as multiplying by 2. So minus 2x. Add a 2x to both sides. Add a 3 to both sides. And notice I always line up my constants and my x terms because that helps me see those cancel and those cancel. 2x plus 2x is 4x. Greater than or equal to 12 plus 3 is 15. And I can divide both sides by a positive number. X is greater than or equal to 15 fourths. And so that's what? 4, 8, 12. So 3 3/4. Because 16 fourths is 4. So we have 0. 3 3/4. Greater than or equal to, put a square bracket. Fill that in. And go from there. Set notation, 15 fourths, positive infinity. And I mean, you could have written 15 over 4 here. I just think it's more, and we can kind of see better when we have a mixed number, but there's no need to convert to a mixed term. Okay. So we're going to get more practice with those as we introduce kind of these other types of inequalities. So we have what are called compound inequalities. And for these we have two kinds. We have or, so that's when one, the other, or both inequalities are true. And we have and, where one and the other are true. So let's say we have 3x minus 2 is greater than 7, or 2 times 1 minus x is greater than or equal to 1. So we're going to essentially solve each of these separately, and then we're going to put them together on our number line. So we need both 3x minus 2 greater than 7. So go ahead and add a 2 to both sides. So we have 3x greater than 9, divide by 3. X is greater than 3. Or go ahead and we have a couple options here. Why don't we just divide by 2 to begin with? 1 minus x is greater than or equal to a half. I'm going to add the x there and subtract the half over here. So add x, minus a half, minus a half. 1 minus a half leaves us with a half is greater than or equal to x. And because my brain likes to see the x on the left, I'll rewrite it as x is less than or equal to 1/2. Because that's the same as 1/2 is greater than or equal to x. But this one just kind of helps me see it better for the number line. So for this one, we have from 3, x is greater than 3, or x is less than a half. But not just less than or equal to. So 0, a half, less than or equal to means we have a square bracket, and it goes this way. And so to combine those into one number line, oh, and that's, I put that 0 in the wrong place. That 0 should be over here, because a half is definitely bigger than 0. So I'll put my 0, put my half, and then based on scale, my 3 is going to be about there. I'm not going to check on how close to scale your number lines are. As long as the main idea is there, you'll be good. So 0, so we have x is less than or equal to a half. And x is greater than 3. So that means as long as we pick a number from over here or over here, one of these will be true. And so or just means treat the two kind of separately, and then we put them onto the number line together. I'll give you a new piece of paper. So consider another example. X minus 1 over 2 is greater than x over 3 minus 1, or 2x plus 5 over 3 is less than or equal to x plus 1 over 6. We can multiply both sides by a non-constant or by a non-negative number. So I'm going to multiply by 6. So divide by 2 times 6 is the same as multiplying by 3. 3x minus 1 is greater than, distribute, 6 divided by 3 is 2. 2x minus 6, distribute, 3x minus 3 greater than 2x minus 6. Subtract that 2x from both sides and add a 3 to both sides. Those cancel, those cancel. 3x minus 2x is just 1x greater than negative 3. And then with our other one, it turns out we can multiply both sides by 6 again. And we end up getting 2x plus 5 less than or equal to 6 divided by 6 just leaves us with x plus 1. Distribute that. We have 2 times 2, which is 4x plus 10 less than or equal to x plus 1. Subtract x. Subtract 10. 3x is less than or equal to negative 9. 1 minus 10 is negative 9. Divide by 3. X less than or equal to negative 3. So here we have x greater than negative 3. 0, negative 3. We have a parenthesis going that away. And x less than or equal to negative 3 means we have 0, negative 3. But now we have a square bracket. And this away. And if we combine the both of these into one number line, well, this is everything to the right of 3, but not negative 3. And this is everything to the left of negative 3 and negative 3, which means we end up having the entire number line (0, negative 3), and we don't have to exclude anything. So here we have the whole number line between negative infinity and positive infinity. And so I said there were two kinds of compound inequalities, the second being and. So if we consider another example, we have, for example, 3 times x plus 1 minus 2 greater than or equal to 4, and 3 times 1 minus x plus 13 is greater than 4. We want to know where they're both true. And so we can work on them each individually. Distribute the 3. 3x plus 3 minus 2 greater than or equal to 4. We can combine those. 3x plus 1 is greater than or equal to 4. Subtract 1 from both sides. 3x greater than or equal to 3. Divide by both sides by 3. X greater than or equal to 1. And go ahead and distribute. 3 minus 3x plus 13 is greater than 4. Negative, I'm going to combine these constant terms. Negative 3x plus 16 is greater than 4. Subtract a 16 from both sides. Negative 3x greater than negative 12. if I divide by -3, we have to flip it. So if x less than 4. And so on a number line, this looks like 0, 1, a square bracket, and to the right. X less than 4 looks like 0, 4, a parenthesis, and everything left. And we want to know where it's both of those conditions are true. So to the right of or equal to 1, and to the left of or not quite equal to 4. And so we can also see that if we combine those two number lines, 0, 1, 4, we have a square bracket at the 1, we have a parenthesis at the 4, and everything in between. And we can look at one more example like this, where we have example 5 times x plus 2 plus 7 is less than 2, and you'll notice I always write and or in all caps. That's just so that it sticks out and I remember to take care of it. 2 times 5 minus 3x plus 1 less than 17. So distribute 5x plus 10 plus 7 less than 2, 5x plus 17 less than 2, 5x, subtract a 17 from both sides, is less than negative 15. Divide by 5. X less than negative 3. And distribute 10 minus 6x plus 1 is less than 17. Negative 6x plus 11 is less than 17. Negative 6x is less than, what happens when I subtract 11 from both sides? 6. Divide by negative 6. And we get x, remember to flip, is greater than negative 1. So let's look at a number line. 0, negative 3, a parenthesis, and everything to the left. Or over here, we have 0, negative 1, a parenthesis, and everything bigger. And if I would draw these on the same number line, it looks like this. Negative 3, negative 1. So what numbers are both here and here? No number is both less than 3, negative 3, and greater than negative 1. So here, the solution set is empty. We have a symbol for that. It's a 0 with a line through it. That's the empty set. Just put that in like parentheses off to the side. So here, the solution set is empty. And we can only get an empty set solution when it is inconsistent, never true, or when we have an and, so the empty set means that it's inconsistent. It is never the case that this is true and this is true. It can't be the case that both are true. And so working with more and or ors, which you'll see in the homework, I think will make that a little bit more comfortable. Now we just have two more types to look at. We have conditional inequalities. So it looks like this. If x is between 3 and 7, then A, where is 1 minus 3x between? Or in other words, if x is between 3 and 7, 1 minus 3x is between what? And so we start with our given, 3 less than x less than 7, and we perform equivalence preserving operations until we have the target in the middle. Well, what does that mean? I was given that x is between these, and I want to know what 1 minus 3x is between. And so first, I'll multiply by negative 3. Multiply negative 3. So I'm going to get negative 9, and notice a negative means I have to flip greater than x, greater than negative 21. And then I can add 1. And so just like if I were doing an equivalence operation, I'd have to do it to both sides. Here I do it to all three parts. So I have negative 9 plus 1. Oh, I lost my negative 3 there. It's greater than negative 3x plus 1, which is greater than negative 21 plus 1. So we have negative 9 plus 1 is negative 8 is greater than, and I'll just rearrange it so it looks like our target. 1 minus 3x is greater than negative 20. But we need to be careful. I'll use red to point it out. We wanted a less than 1 minus 3x less than b. But notice these are greater thans. So let's rewrite that. Negative 20 less than 1 minus 3x less than negative 8. And so since now these line up, we know that 1 minus 3x is between a equals negative 20 and b equals negative 8. And for this would be the answer. And so really conditionals, it's just saying if we know that x is between some values, what are our bounds or limits of some other inequality or expression involving that same x? And so those are really just bringing up together those equivalence preserving operations, but working in the opposite order. Now we only have one other type of problem to look at. And those are, for these, whenever we have rational or power expressions, so that's, for example, if we have fractions or polynomials, we're going to use the test point method. And so let's say, for example, x squared minus 8x plus 7 is greater than 0. Well, let's go ahead and factor. And what we have is two things that multiply to give us positive 7 and so we have negative 1 and negative 7 multiply to give me 7, but add to give me negative 8. And what we're going to do next, so this is asking, when is this product greater than 0? And greater than 0 is the same as asking, when is it positive? So what we're going to do is we're going to draw a number line. And we're going to plot where it equals 0. So it'll equal 0 if x equals positive 1. And it'll equal 0 whenever x is equal to 7. Right? So it equals 0 at those 2 points. And so what we need to figure out is whether it's positive or negative here, whether it's positive or negative here, and whether it's positive or negative here. And so what we'll do is we'll construct a table. So what we have is our test interval. So we want to know what happens between negative infinity and 1. We want to know what happens between 1 and 7, and between 7 and positive infinity. And then we'll go ahead and just pick a test point within that interval. So this 0's in the first interval, 2's in the second interval, and 10's in the third interval. You can pick any point you like, it doesn't matter which. And then let's look at the sign of that expression. So sine of x minus 1, x minus 7. Well, when x equals 0, we have 0 minus 1, which is a negative, times 0 minus 7 is a negative, and so that's a positive. If we pick our test point of 2, we have 2 minus 1, which is 1, or positive, and 2 minus 7, which is negative. And a positive times a negative is a negative. And then if we pick 10, 10 minus 1 is 9, which is positive. And we have 10 minus 7, which is 3, which is positive. Positive times positive is a positive. And so this is where we look back at our original. So we want to know where x minus 1 times x minus 7 is greater than 0, where this is positive. Well, we said it's positive here and here, which means our solution is negative infinity to negative 1, or to positive 1, or, and this is our union symbol to put two sets together, 7 to positive infinity. And on a number line, right, that'll look like a parenthesis here and a parenthesis here, and then shaded in on the outside, with this interval representing this part and this one representing this part. And so let's go back and look at what we did. Well, we already had it equal to 0, so if it isn't, we're going to want it. So first we get one side equal to 0. Then we factor. Then we plot zeros on the number line. Then we construct a test point table. And then we graph the solution set and write intervals. So you could do this in either order, but as long as you do both, you'll be good. So let's look at another example. In all of my examples, I'm going to have it equal to 0. That wouldn't need to be the case, or I already have one side equal to 0, but we get it equal to 0 if not. And this one's actually not too bad because we have x plus 4 times x minus 1 times x plus 2 is less than or equal to 0. And so our first step is get one side 0. Well, that's already done. Then we factor. Well, that's already done. So now we have to plot the zeros. So draw a number line. This equals 0 if x equals negative 4, if x equals 1, and if x equals negative 2. And so we'll go ahead and put those points, negative 4, negative 2, and 1. And we construct our test point table. Test point table. So we have interval, test point, and sine of x plus 4, x minus 1, x plus 2. So I have this first interval from negative infinity to negative 4, and then from negative 4 to negative 2, and negative 2 to 1, and then 1 to positive infinity. A test point here, negative 5, negative 4, negative 2, we'll use negative 3, between negative 2 and 1. I pick a 0. Whenever I can pick 0, I'm going to pick 0 because it tends to be easy to work with. And 1 and infinity, you can just pick 10. It doesn't really matter. So if we take negative 5 here, negative 5 plus 4 is negative 1. So we have a negative times negative 5 minus 1 is negative 6, also a negative. Negative 5 plus 2, also negative. So we have negative times a negative times a negative, which is negative. And if you want, you can go back and put those lines up here on your number line. If we pick negative 3, here x plus 4, negative 3 plus 4 is 1, so that's positive. Negative 3 minus 1 is negative 4. And negative 3, I said that wrong, didn't I? Negative 3 minus 1 is negative 4, yep. And then negative 3 plus 2 is negative 1. So we have a positive times a negative times a negative, which is a positive. And then for negative 2 and 1, if it's 0, 0 plus 4 is positive, 0 minus 1 is negative, and 0 plus 2 is positive. Positive, negative, positive. It means that that one is negative. And then our last one with 10. 10 plus 4 is 14, which is positive. 10 minus 1 is 9, is positive. And 10 plus 2 is 12, is positive, which means they're always positive. And so I had a negative, I had a positive, a negative, and a positive. And after test point, we graph solutions. So 5, graph solutions. So we'll put our negative 4, negative 2, and 1, and you could work on that same one up there. And we want to know when this product is less than or equal to 0. So when it's negative. Well, we said it's negative here, or equal to 4, negative 4. It's positive here, and then between negative 2 and 1, it's negative. And then over here it's positive. And so that means our solution set is negative infinity to negative 4, square bracket, because it can be equal to 0. If this were just less than 0, we would have to use a parenthesis here, because we'd have a parenthesis here. Union, negative 2, 1, square bracket. And that's our solution. And so we'll go ahead and look at just 2 more examples. One where we have a fraction but we don't have to factor, and then one where we do. So if I have x minus 1, x plus 3 over x minus 2, when is that negative? So we need to find our zeros. So that's when x equals 1, when x equals 2, or x equals negative 3. Negative 3, 1, and 2. And then we need to construct our test point table, so our interval. We have from here to here, negative infinity to negative 3. We have from negative 3 to 1, negative 3 to 1, from 1 to 2, and then 2 to positive infinity. Within each interval, we need a test point. So let's pick negative 10, 0. Unfortunately, between 1 and 2, there isn't a nice neat one, so we can use 1.5, and 2 to infinity, we can use 10. And now we need the sign of x minus 1, x plus 3, all over x minus 2. What negative 10? We have a negative 10 minus 1 is a negative. Negative 10 plus 3 is still negative. Over negative 10 minus 2 is still negative. So we have a negative times a negative, which is a positive, divided by a negative. It's a negative. We try our test point 0. We get a negative. 0 plus 3 is positive. 0 minus 2 is negative. Negative times positive is a negative. Divided by a negative is negative. 1.5. 1.5 minus 1 is positive. 1.5 plus 3 is positive. 1.5 minus 2 is negative. So we have positive times positive is positive, divided by a negative is negative. And then our last point, 10. 10 minus 1 is 9, which is positive. 10 plus 3 is 13, which is also positive. And 10 minus 2 is 8, which is also positive. I noticed something. So let me finish that. Positive, positive, positive is positive. I said negative times a positive is negative, divided by a negative is positive. It's like, well, if that's negative, and that's negative, and that's negative, it's not the case that it couldn't be true, but if you see 3 negatives or 3 positives in a row, you might want to double check because you might have made a mistake. Not a guarantee, but I was just like, that seems uncanny. And so here we have negative, positive, negative, positive. So negative, positive, negative, positive. And we wanted to know where it was negative. And so we have from here to here. But it can't equal 0 this time, so we have a parenthesis. And so from here to here, and that's it. And so to write that in interval notation, we have negative infinity to negative 3, union together with 1, 2. And that's our solutions. And then we'll go through one last example for today. Here we have x squared minus 9 over x squared minus 64 is less than or equal to 0. So remember, we have to first get it equal to 0. We're there. And then we have to factor. X squared minus 9 factors into x minus 3, x plus 3, and x minus 64 factors into x minus 8, x plus 8, less than or equal to 0. We'll plot our zeros. So we have positive 3, negative 3, positive 8, negative 8. So 3, negative 3, 8, negative 8. And then for our test point table, so we have our test interval. We have negative infinity to negative 8, negative 8 to negative 3, negative 3 to 3, 3 to 8, and 8 to positive infinity. So choosing our test points, negative 10, negative 5, 0. You don't have to pick symmetric points. I typically do just because I then have to do a little bit less thought in double checking my multiplication. And then we need to look at our sign. So negative 10, so sign of x minus 3, x plus 3, x minus 8, x plus 8. So at negative 10, we have a negative, a negative, a negative, and a negative. So we have negative, 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 negative. So we have a positive over a positive, which is positive. At negative 5, we have a negative and a negative, and a positive. So negative, 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 positive. So negative times negative is a positive, divided by a negative is negative. When it's 0, we have negative, positive, negative, positive. So negative, positive, negative, positive. So a negative over a negative is positive. When it's 5, we have positive, positive, negative, positive, 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 negative, positive. Positive over a negative is negative. And then when x equals 10, we have a positive, 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 positive. So positive, 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 makes that whole thing positive. So we go up here, positive, negative, positive, negative, positive. And this says we want to know when it's less than or equal to 0, so negative or 0. So we can include our zeros this time. It's negative in between. We include our zeros. It's negative in between. So our solution set is negative 8 to negative 3, union 3, 8. So you'll see that a lot of this goes back to drawing our graph of our inequality. And once we draw the graph of our inequality, converting that to our solution set, we have our or at least similar equivalence preserving properties, simplifying, add or subtracting the same expression from both sides, multiplying or dividing by a positive. But if we multiply or divide by a negative, we have to flip the sign. And that was because of that example I showed you where if instead we just added them, the x and the other end up on opposite sides of the inequality. When you're working with the simplest case of just a single inequality, you simplify, graph, and then check a point, shade that in, and then give it inset notation. When we're working with compound inequalities, we have to think about whether it's or and. If it's and, both must be true, but or, only one or both can be true. When we're working with conditional inequalities, we are given a bound on x. We know that x is between some values. And what we do is we apply our equivalence preserving operations to figure out what the bound is on that target expression. And then when we're dealing with anything that involves zeros, so that's our rational exponent, or our rational equations, or our power expressions, we need to check and make sure things can or cannot be included. And now that I've said that summary, I want us to go back and look at something. Our domain of this domain is as long as x doesn't equal 2. Because if x equals 2, the denominator is 0 and it's undefined. So we need to check, did we include a 2 in our final answer? We didn't. The 2 wasn't included because it couldn't be equal. However, our domain here, x can't equal plus or minus 8. Because if x is positive 8, this is 0 and it's undefined. And if x equals negative 8, this is undefined. And so our domain can't be where it's plus or minus 8. So did we include a plus or minus 8 here? Well, we tried to include a negative 8 here, and we tried to include a positive 8 here. So that means this is not our solution. We can't include that negative 8, but we can include negative 3. We can include positive 3, but we can't include positive 8 because this original is undefined if x is plus or minus 8. And so we need to be careful. And if I were to go back to my general sequence of steps, after 5, graph solution set and write intervals, and then 6, compare with the domain. Because we need to be really careful when we have a rational, in particular, the denominator can't equal 0. So even though my entire fraction could, this is undefined when it's equal to 8, or when it's equal to positive, or negative 8 or positive 8. So, I'll see you in the next video, everyone.